This is my section 5.5 practice question 277 video vlog. So this is the final, section that introduces a test that we can use on a series to determine its convergence or divergence. And this is the alternating series test. So the one thing that is essential for this test to be conducted or to be used, and it can only be used, if the function is set up this way, only this test can be used to determine whether the series converges or diverges. And for us to know whether or not a series is appropriate to be tested using this alternating series test is if a series can be put into a form where the series is -1 to the power of n plus 1 times n over 2 to the power of n. Sorry, I don't know why I just said that. If the form is -1 to the power of n plus 1 times b sub n. So in this, we have a b sub n already given to us. And what we're doing is essentially trying to use that b sub n to figure out what the comparison function is, and then determine the alternating series, determine whether or not the alternating series converges or diverges. So I know I messed this up again, but the form can be -1 to the power of n plus 1 or just to the power of n, and then b sub n is the second function within the first function. So if it's already in that form, a series is said to converge if the b sub n plus 1 term is in between 0 and b sub n for all elements past the first element. And the limit of the b sub n equation has to equal 0. If both of those conditions are true, then the alternating series converges. If it doesn't, then it diverges. So again, this is just another way to tell whether or not a series is converging or diverging. And this can, again, only be used if it is in the form of -1 to the power of n or n plus 1 times b sub n. So what you want to do if you already see something in a form where it has -1 to an exponent is try to get it into the form where you can use the alternating series test to test the convergence or divergence. Along with that, there is a thing called the remainders in an alternating series, and that is essentially just that in an alternating series, if S, let's say S is the sum of the series, S sub n would be the partial sum of the series, and the remainder, we can call that R sub n, would be the sum minus the partial sum, so S minus S sub n, that would be the remainder. So R sub n equals S minus S sub n, and it has to satisfy the condition that the absolute value of that remainder is less than or equal to the b sub n plus 1th term, whatever that value is at b sub n plus 1. So that's just verifying remainders, or if you have an alternating series and you have the partial sum, you can use that to find the nth partial sum and check that remainder condition to make sure that it is actually a remainder. And I guess from there, that it's like a two-part process. That's just for guessing the remainder of the alternating series. From the remainder, we can actually calculate whether or not it's like an absolute or conditional convergence, I believe. Sorry, no, I was completely off. Estimating the remainder of an alternating series is just another it's just another way to estimate like a bound for the series. There is going to be an error with the approximation, and we can approximate the series using the partial sum at the same time. Like, say we're trying to find the remainder estimate at R10, we can use the partial sum at S10 to calculate the bound. Yeah. So pretty much all we're doing here is like, how do I say it? We can use that remainder formula that I said, like the absolute value of R sub n has to be greater than, or has to be less than or equal to B sub n plus 1, so the n plus 1th term. So again, if the R value is like or if we're trying to estimate at like the 10th part, we can do R sub 10 has to be less than or equal to B sub 11, and we just evaluate what the B sub n series is at its 11th element. And then from there, like if that is true, then we can determine the bound of the error, like what the approximation is versus like the more accurate determination of the value. Moving on from there, I actually brought this up in one of the earlier videos, but this is where we start going into whether it's an absolute convergence or a conditional convergence. I may have gotten it wrong in my previous video, but just for the record, an absolute convergence is when a series A sub n and its absolute value, so the entire value of the series at like absolute value of it, are the same. Like if they both converge, then it's absolute convergence. But if A sub n converges and A sub n, like the absolute value of it, diverges, then it's conditional convergence. There's no such thing as like absolute or conditional divergence, though. Well, not at least that we've learned about. But absolute convergence does imply that both the functions will converge, of course, but we need to obviously perform tests to tell whether or not it converges absolutely or not, and all we would have to do for that is just put the entire series in absolute value and make a comparison to see if they converge. Yeah, so again, it's a two-part process. You have to take the absolute value of the given series, and then you have to perform a comparison test on it of your choice, series test, alternating series test, p-series test, limit comparison test. You can pretty much choose again. But again, depending on what you get for A sub n and the absolute value of A sub n, that tells you whether it's absolutely or conditionally converges. So I believe that is pretty much what chapter 5.5, section 5.5 entails in regards to moving forward. It provides us with that last comparison test for alternating series, and we can now also use that to determine whether a series is converging or diverging, and further from that, we can tell now whether it is conditionally or absolutely converging. And the question that I chose here was question 277 from the practice problem set. And again, this was just a random choice, but this is actually a pretty formidable question. I believe it's the series as it goes from 1 to infinity, cosine of n times pi, like n times pi within cosine, all over n to the power of 1 over n. So the first thing I'm going to do is try to see if I can put this into an absolute, if I can put this into a alternating series form. At least that way I'll be able to use the alternating series test to figure this out. So the first thing we're going to do is um, I might need to look at something. And okay, so I was trying to see how cosine n times pi went, like how it progressed forward, and it is actually an alternating series. Cosine of n times pi equals -1 to the power of n for all values of n as it goes like forward, or I guess even backwards, like -pi, like, I mean, second, sorry. Yeah, so it will always alternate around -1, will either be -1 or 1. So we can rewrite that, I believe, where it would be the summation of n to infinity equals -1 to the power of n times 1 over n to the power of 1 over n. Yes, okay. So far I've gotten this much. I pretty much went from this original function to this function, and I figured out the cosine alternating series by, again, just plugging and chugging random numbers and seeing that it did, like, as n just went from 1 to 2 to 3 to whatever, it just alternated around 1 and -1. So from there, I just wanted to rewrite it where it would be in the alternating series format. And then from here, we have our b of n function, which is the 1 over n to the power of 1 over n. And even though we call it b of n, it is technically, I guess, like our a of n for whatever comparison test we're moving forward, but I'm just going to keep it labeled as b of n. And since we're trying to find a comparison to this I can say that 1 over n can equal c of n, and the relationship they have is that the original function b of n, 1 over n to the power of 1 over n, will always be greater than 1 over n as it progresses through, because again, it will the n to the power of 1 over n will always have a larger or it will have a smaller denominator, which results in a larger overall value as the series progresses forward. So once we set that up, we can compare 1 over n. We can see that 1 over n is already in the form of like a p-series test, and in this example, we can say that 1 over n, the p is equal to 1, and since it is equal to 1, it has to diverge, because again, if you remember, in a p-series test, it cannot be even equal to 1, it has to be less than 1. So since p is 1, both of these series diverge. And because of the comparison test and the p-series test, we can say that the original function and the new function both diverge. If we want to test for conditional or absolute divergence, I'm actually just going to go ahead and do that. It didn't ask me to, but absolute value of this entire function say at like 3, it would be I'm sorry. That was so dumb of me. Both of these series diverge. There's no testing for convergence. I was trying to shoot so forward that I just lost the definition of the test. But yeah, so since both of these series diverge, there's no testing for absolute or conditional convergence. That is pretty much the end of the question as well. As you can see, we went from the original formula to the alternating series form of the equation. We used the portion of the alternating series as the first equation, the b of n, and then we found an alternating series close enough to it, which was just 1 over n. We realized that the original b of n is greater than 1 over n over the interval. And since 1 over n has a p-series value of 1, it diverges, as well as the original function also diverges. Yeah, that is pretty much it, and I hope that was a pretty good sum up of section 5.5. Thank you.